6.10 Rate balance for control volumes at steady state. We are going to take a look at entropy balance for open systems. The open systems or control volumes allow mass transfer across the system boundaries. We are already familiar with energy balance for open systems. This is our system. Energy going in and energy is going out of the system, and there will be energy change inside the system. So we can write energy in minus energy out equals energy change in the system. It can be also expressed in rate form. So energy balance equation in the rate form. Similarly, we can write entropy balance for open systems. Entropy going in and entropy going out of the system. And there will be entropy change in the system. So we can write entropy going in, entropy going out of the system equals entropy change in the system. But note that entropy is not conserved due to the irreversibility. So there will be entropy production in the system. So we need to add entropy production. So net entropy transfer in minus net entropy transfer out plus the entropy production within the system is equal to the change in entropy of the system. It can be also expressed in rate form. The general entropy balance equation for control volume at steady state is expressed here. So take a look at the equation. The left-hand side of the equations, it may have ds over dt. ds over dt describes the change of entropy within the control volume. At steady state, it drops out. The right-hand side of the equations describes the entropy transfer across the boundary and the entropy generation or entropy production. The summation is used to include all inlets and outlets in the control volume. At steady state, ds over dt drops out. There is no change with time of the entropy within the control volume. For steady flow devices such as turbines, compressors, pumps, and nozzles, the rate of entropy change with time becomes zero. Recall that energy is transferred by mass, heat, and work. Energy transfer by mass, heat, and work. But there are two entropy transfer mechanisms: mass transfer and heat transfer. Entropy transfer by mass and heat. So note that entropy is not transferred by work. First, let's take a look at entropy transfer by heat. Q dot over T represents the rate of entropy transfer by heat. So Q dot is the rate of heat transfer through the system boundary. T is the temperature at the location where heat transfer occurs. Heat transfer and entropy have the same directions. Heat transfer to a system increases the entropy of the system. Heat rejection from a system decreases the entropy of the system. If the system goes through an adiabatic process, Q is 0. Entropy is also transferred by mass. Mass carries entropy. So these two terms describe the entropy transfer by mass. For a closed system, we do not have these terms. They are related to the entropy transfer by mass. Entropy of a system increases when mass is going into the system. Entropy of the system decreases when mass is leaving the system. And the last term describes the rate of entropy production. Entropy production is due to the irreversibilities such as heat transfer through a finite temperature difference and friction. For a reversible process, entropy production becomes 0. If a system has one inlet and one exit at steady state, the entropy balance is simplified as this. Okay, let's see an example. Steam enters a turbine with a pressure of 30 bar, a temperature of 400 degrees Celsius. So pressure, temperatures are known. So we can fix a state at the inlet and velocity of 160 meter per second. Saturated vapor at 100 degrees Celsius exits. So at the inlet we have steam or superheated vapor. At the exit we have saturated vapor. The quality is 1. And the temperature is given 100 degrees Celsius. We can also fix the state at the exit. Velocity of 100 meter per second. At the steady state, the turbine develops work equal to 540 kilojoule per kilogram of steam flowing through the turbine. Heat transfer between the turbine and its surroundings occurs at an average outer surface temperature of 350 Kelvin. Determine the rate at which entropy is produced within the turbine per kilogram of steam flowing in kilojoule per kilogram Kelvin. Neglect the change in potential energy between the inlet and exit. So steam turbine produces work. The rate of entropy production associated with the process is to be determined. Steam turbine operates at steady state. There is no change in property with time. We take the turbine as the system. So this is our system. Mass enters and leaves the system boundary during the process. There is only one inlet and one outlet in the control volume. So the mass flow rate at the inlet or location 1 is equal to mass flow rate at the outlet or location 2. So we can write mass flow rate at location 1 equals to mass flow rate at location 2 or at the exit. We simply write m dot. We can also write the entropy balance equations at steady state. We divide the equations by the mass flow rate, m dot. In these equations, the heat transfer rate Q dot is unknown. To determine the Q dot, we are going to apply the energy balance. The energy conservation principle can be applied for any process. The general energy balance equation is written as it operates at steady state, so this term drop out. We neglect the potential energy change between the inlet and exit. So this cancels out. And divide the equations by m dot. The work produced by the turbine is given, and the velocity at the inlet and exit is given. As we know, two independent intensive properties, we can fix the states at the inlet and exit. So the enthalpy can be also determined. Let's first determine the enthalpy at the inlet. At the inlet, we have 30 bar and temperature 400 degrees Celsius. At 30 bar, 400 degrees Celsius. Enthalpy at the inlet is here. At the exit, the temperature and the quality are given. So we use table A2. Saturated water. At 100 degrees Celsius, quality is 1, saturated vapor. So enthalpy for saturated vapor is here, H2. So going back to the energy balance equations, plug in values, we can solve it for the heat transfer rate, Q dot. So the rate of heat transfer per unit mass of steam is negative 22.6 kJ per kilogram. The negative sign indicates heat is removed from the system. So going back to these equations, so we just got Q dot. We also need the entropy values at the inlet and outlet. At the inlet, 30 bar and 400 degrees Celsius, entropy is here. At the exit, 100 degrees Celsius and saturated vapor, entropy is here as 2. Also note that T sub B is the temperature where the heat transfer occurs. It is given as 350 Kelvin. So be careful to use the correct temperature. So plug in values, we can get the entropy production. So this is the rate of entropy production per unit mass of steam, as steam is flowing through a turbine. It is caused by the heat transfer and mass transfer to the system.